Today we're talking about buffers.
Uh-oh.
We're talking about buffers. So let's define a buffer first. A buffer.
Are you recording?
Yes, I am. Thank you. A buffer is a solution that resists. You're going to get to see this in lab, I think, next Friday. Changes in pH when either a small amount of acid or base is added to it. Usually a buffer solution is made from a weak acid and one of its salts, which is just the conjugate base. So you'll hear a salt interchangeable with the conjugate base a lot. The salt is what you end up with. Or vice versa, with a weak base and its conjugate acid or salt. One example would be ethanoic acid, which is a weak acid, and sodium ethanoate, which is one of its salts, right? Sodium ethanoate is a salt. The ethanoic acid acts as the acid in the buffer solution and will absorb any base added. So let's do a quick little equation for what that would look like. So if I have CH3CO2H, so that is ethanoic acid, plus, let's say I'm adding OH to it, which would be a base. Agreed? OH minus. You guys okay with that? That's going to be in equilibrium with CH3CO2 minus plus what? Water. Because what happened here? This hydroxide ripped off a hydrogen from the ethanoic acid. Yeah, you got it. So this hydroxide is gone, and now we have water. It's key to know that we used up all of the hydroxide to make the water. That's important later. In the following, the ethanoate ions, the next one we're going to write, act as a base in the buffer solution and absorb any acid that's added. So this is going to be the other way around. So now I have to start out with CH3CO2 minus plus, what am I going to be adding to this? H3O plus. Hydronium plus H3O plus is in equilibrium with what? H2O is one of them, plus CH3CO2H.
Yeah.
So that's just kind of the opposite. The process of mopping up of added base or acid keeps the pH unchanged. Underline those three words. A good buffer will keep the pH essentially the same. So I'll be able to add in an acid or add in a base, the pH stays the same. Added more acid, the pH stays the same. The better the buffer, the more consistent the pH stays. And like I said, you're going to get to see that in lab next week. A crucial part of the application of buffer solutions on the AP test is the fact that buffer solutions are inadvertently produced during the titration of a weak acid or weak bases. So weak acids and weak bases are where your buffer solutions are going to come from. You're not going to see a buffer solution of a strong acid. Why? What's a strong acid do? Completely dissociates, right? I need to have something on both sides that can either eat up or take away an acid or a base. That's why a weak acid is what we want. So, as Bill and I would say, please consider the following. Titration of weak acid with a strong base. As the base is gradually added to the weak acid, some of the weak acid is neutralized, and the result is the salt of the weak acid, which is the conjugate base in water. Because not all of the weak acid has been neutralized, the neutralization is only partly done. It's partial. It's still present in solution with the salt. So you still have some of the original weak acid with the salt, which is why weak acids are important to use. This combination of solution is what a buffer solution is. And its pH can be calculated by first determining the remaining concentration of the weak acid, then with the new concentration of the salt, and applying what we're going to learn, the Henderson-Hasselbalch equation.
Ooh, wow. That sucks.
Sounds like David Hasselhoff, but it's not. All right, it's Henderson-Hasselbalch. If I titrate a weak base with a strong acid, it's the opposite. As the acid's gradually added to the weak base, some of the weak base is neutralized, and the result is the salt of the weak base, its conjugate acid, and water. Because not all the weak base has been neutralized, the neutralization is only partial. It's still present in solution alongside the salt. So, on this one, I could determine the pOH, and then use the Henderson-Hasselbalch equation. Flip it. Let's talk about the Henderson-Hasselbalch equation. So the pH of a buffer solution is determined by the pKa
Yeah.
or pKb of the weak acid or base and the ratio of the concentrations of each component. To calculate the pH of an acidic buffer, use one version of the Henderson-Hasselbalch equation. So I'm going to give you what the two versions are. They're the same, but you'll see it both ways. So here we go. Most important equation for buffers. pH is equal to pKa plus the log of the concentration of the salt over the concentration of the acid. Concentration of the salt over the concentration of the acid. This is for if it's an acidic buffer. Or, you can see it like this. pH equals pKa plus log of the concentration of A minus over the concentration of, what'd be on the bottom here? See if you guys can get this. What's going to be in the bottom? If this is A minus, what's the bottom going to be? HA, right? HA.
Yeah, right.
The acid, right?
Of course. Obviously.
The acid, yes? Because the acid wants to do what with that proton? It wants to donate it. So here's the original acid, that's my salt.
And when it gets rid of it, it becomes A minus.
Correct.
The conjugate base.
Correct. Yes. You got it. Or the salt.
Is the salt just a conjugate acid or base?
Yeah, for if it's acidic, it's going to be the conjugate base,
Okay.
also known as the salt. For a basic buffer, pH is going to equal pKb plus log of concentration of salt
Over base.
divided by concentration of base. Or pH is going to equal pKa plus log pKb, thank you, pKb plus log concentration of BH minus, right, divided by what?
B.
B, divided by concentration of B. So those are the two versions of Henderson-Hasselbalch. Then you can apply 14 equals pH plus pOH. So then once you get that, then you can do all the other stuff we've already done. And a lot of times you have to ice it even to get to this point, which I'll show you some examples.
Wait, so for the basic buffer would be pOH equals that?
Oh, shoot, you're right. pOH, good catch. All right, that'd be
Okay.
pOH. Let's fix that. pOH. Thank you, Ashan. It's basic, so it would be pOH, good catch. Since pKa or pKb is fixed for a weak acid or base, if the concentration of the components of the buffer are changed but remain in the same ratio, the pH of the buffer will not change. Look at it. I mean, if they're in the same ratio, yes,
It's just less than.
it's just a smaller ratio. It's the same ratio. However, changing the concentrations of the components will change the capacity of the buffer. A little knowledge of logs when you're doing this will go a long way. You know, the math logs. Not like the wood logs,
Oh, man.
the math logs. If you look at the acid version of the Henderson-Hasselbalch equation, it can be seen that if the pH, let's just say of, not or, a buffer, the pH of a buffer solution, is greater than the pKa of the acid. If that is true, then the term concentration log of my salt, here's my concentration of salt over my concentration of acid, right, must be a what type of number? Positive number. You got it. In order for the log of a number to be positive, then the number, in this case, concentration of salt over concentration of acid, must also be what? Greater than 1, right? It must be greater than 1.
Greater
So-
than 10?
I don't think greater than 1.
Okay.
Hold on. It's been a long.
It just can't be negative.
Okay.
I can.
I think it has to be a positive number.
At the beginning of the center period,
That's natural.
and then it'll.
Shouldn't be greater than 10.
Wait, for it to be positive.
Bigger.
For it to be positive.
Can it be?
Yeah, 'cause log of 1 is 0.
Log of 1 is 0, so it has to be greater than 1. Yeah, we're good.
Okay.
We're good. It has to be greater than 1.
Oh, yeah. We should start thinking.
Like I said, if you're good at logs, this will make more sense. It's okay if you're not. Alright, it's okay if you're not. But I'm still going to finish this little thought. So the salt concentration must be greater than the acid concentration, right? In order to get it greater than 1. So when the pH is less, the opposite's true. In both. The partial neutralization, that's definitely a really small line to write that big word. Neutralization scenarios described above. A crucial point is reached. A crucial point, underline that. When the weak acid or base,
Yeah.
what are we doing over there?
Yeah, guys.
Has been
You just shout back.
exactly half neutralized. Guess where it's going to be half neutralized? Aha. Or when the titration is exactly halfway to the equivalence point. Halfway to the equivalence point. At this point, the concentration of salt and acid and base are equal. So, concentration of salt over concentration of acid, and for the other one, concentration of salt over concentration of base would both equal 1. The log of 1 is 0, which simplifies Henderson-Hasselbalch to mean at the midpoint, pH equals pKa.
That's nice.
That is sweet.
What's the midpoint?
All right?
What's the second
The midpoint is the halfway to the equivalence point. Remember the titration curves? Right? So the titration curve looked like this, up, over.
Yeah.
The midpoint is halfway to this. So at the midpoint, pH equals pKa. That is so important to know, right? Because this will save you a lot of work. That will save you a lot of work. Using the relationship between pH and pKa lets us look at quantitative and qualitative things to determine which component of the buffer is there in the greatest concentration. A protein side chain that has an amine group that can be protonated, which means we're just getting another H, right? Getting another H, can become NH3+, thus becoming the what in a buffer? Acid in a buffer, or unprotonated. Unprotonated as itself, NH2 would be the base. When an H plus ion moves around in this manner, it's kind of swings both ways, right? Yes, and go either way. This is called labile.
Huh?
Labile. All right, which means it can just kind of move between the two. New word for you today. All right, fun chemistry word. It's kind of like the resonance of the hydrogen. Yeah, no, it's kind of. It's not resonance. What?
That's different from like how water.
Water's amphoteric. we're saying that hydrogen here is labile. It can go between NH2 and NH3 very easily. It's flipping between the two. Labile just means it can move. We can compare pH to pKa and determine what species is predominant at a certain pH, or use the ratio of components to determine the pH. So now we've got multiple ways to get pH. It kind of depends on what makes sense to you. Flip it. Here we go. This is it. All right? This is it. Number one. Yeah, that's where I get these examples from. A 0.10 molar solution of ethanoic acid, Ka, 1.8 times 10 to the fifth, is mixed with a solution of 0.10 molar of potassium ethanoate. Calculate the pH of the resulting solution. So, number one. It's going to be better just to work through these together so you have some good examples, I think, in your notes.
That's a
All
very
right.
good idea.
Instead of you trying to do it by yourself. If you want to try to do it by yourself, work ahead, that's fine. Calculate the pH of the resulting solution. So, first of all, do we have a buffer here?
Wait,
Is potassium ethanoic?
I want to say probably.
Is ethanoic acid a weak acid? Is that a weak acid?
Yes.
Is potassium ethanoate the salt of that?
Sure.
Yeah, it is. So yes, we have a buffer.
So,
Sure.
All right, so we've answered the first question. Yes, we have a buffer.
okay.
If we have a buffer, we can use Henderson-Hasselbalch. Henderson-Hasselbalch. Henderson-Hasselbalch, right? So hold on here. We know in the Henderson-Hasselbalch my concentration of salt, right, over my concentration of acid, right?
Yeah.
It's going to equal what here?
1.
1. And I know that the log of 1 is equal to 0, which means
I can't be looking at that. That confuses me.
what?
1 equals 0.
The log of 1 equals 0.
You know,
So based on the Henderson-Hasselbalch equation, sorry. So log of 1, yes.
Yes.
This means that pH is going to equal pKa. My pH is going to equal my pKa based on the Henderson-Hasselbalch equation, right?
Yeah.
Yes. So I'm trying to work through these. Well, how would you think through this? So I have Ka. I need to get the pKa of that. How do I get the P?
Wait, negative.
Take the negative log. So the negative log of 1.80 times the negative fifth is what?
Oh, yeah, you can take
Calculator people, listen to you.
I took a P.
4.7?
I got 4.74. Is that what you guys had?
For sure.
Oh, it's 8. Oh, see, I
Yeah.
see.
Sure.
1.80?
That's what I had.
4.74 was my
I just
pH.
did 1.8, so I was going to do 6.
So on that one, I think, okay, it's a buffer. Henderson-Hasselbalch, my concentrations are the same, right? So something divided by itself is 1. Log of 1 is 0. That gets rid of the second part of Henderson-Hasselbalch, which means pH equals pKa.
So you just got to know all the shortcuts.
Yeah. Or you can just do the whole thing and still get the same thing, all right? I'm trying to work these through
Of course.
so you guys can kind of see how they work. Number 2, explain why it's a good practice when selecting a weak acid to make a buffer solution. What is this?
You have to keep reading.
No, thank you. I'm just like, explain why it's a good practice when selecting a weak acid to make a buffer solution. That one with a pKa close to that of the desired buffer's pH is chosen. Why do you want to have one close? Why would that be important?
Great question.
So the pH doesn't change as much.
And why will the pH not change?
It's a buffer.
Because it's a buffer. So we're saying, why is it good practice when selecting a weak acid to make a buffer solution that one with a pKa close to that of the desired pH buffer's pH is chosen? Right, because we know the region of maximum buffering, yes, in that area, at the midpoint, pH equals pKa, right?
Maximum buffer.
The point of maximum buffering is at the midpoint.
Okay.
It's at the midpoint before it goes that spike. So, I said the best buffers. I said the best buffers have approximately a 1-to-1 ratio of acid to what? Salt. Or base to salt, doesn't matter. So they can mop up or absorb, right? Mop up / absorb what is added. So a good buffer can add, if I had an acid, it can mop up the acid. If I had a base, it can mop up the base. That's why the conjugate acid-base pair is so important, right? You have an acid on this side, you have a base on this side. Whatever you add in, it can eat that up. It can eat that up. Ah. Number 3. Let's keep going. Let's just keep going.
Yeah.
A certain biological molecule has an amino group on its side chain with a pKa of 7.6. Calculate the pH that will result in 1/3 of its amino groups being protonated. Looks hard, but it's not. First thing I'm going to do is write out Henderson Hasselbalch. So, pH, we're talking about an acid here, right? Well, I'm going to protonate something. Yes. So we're looking at protons. So pH equals pKa plus log of the concentration of the deprotonated,
No.
right? Would that not be what it would be in an acid, right?
I can't tell you.
Over the concentration of the protonated. Yes?
What is protein?
I'm gonna review the last page.
All right.
Which was rebirthed.
So if we're talking about an acid, deprotonated means I've taken away
A proton.
a proton.
I got that.
Protonated is,
Salt. Okay.
yeah, exactly. Deprotonated would be my what on top? That's going to be my,
Conjugate base.
The
You've
conjugate-
taken away your-
yeah, the conjugate base after the proton's removed.
This is for an acid?
This is for an acid over the original acid, or the salt over the acid. Same
Can you
thing.
not like
Salt of base?
deprotonate for a base?
The conjugate base would be the salt. Yes, remember the salt and conjugate base are the same thing.
So what if it's upside down? and
Chuck in a
it's-
1/3.
It'd be flipped. Yes,
Yeah.
for a base it'd be flipped. You got it. So we know on the. I know lots of words. All right. You just have to figure out what the words mean. But you guys are smart,
Easy.
so you guys can do this.
Yeah.
We know that 1/3 of the amino groups have been protonated. So let's assume one. I'm just going to assume 1. Okay? Let's assume 1. So this is equal to. Let's we sub everything in. 7.6, right? Plus log of what's going to go on the top?
3.
0.67 over 0.33, right? Wouldn't that work?
Wait, can we,
Right?
can we do 0.66?
Because it's one.
Sure.
So it divides
And
better?
the reason you can just assume is because the ratios would be the same.
Yes, you got it.
I don't know what that means.
Oh, you are right.
It's a ratio of
I see that it says 1/3, so that means that
It's
1/3
all
is
coming
salt.
from one.
More like thumbs down.
you could do that too. All right, there's multiple ways you could write this. Okay, but it's basically going to be the log of what? 2. It's going to be the log of 2. So 7.6 plus the log of 2 is what?
7.9.
7.9. Done.
That's just you plug it into your
All
calculator.
right,
I thought you all just like
done.
found that. I was like, yo.
Yeah, I was like, how are you guys doing this?
So once again, that was the same exact thing we were doing, just with different words. Okay?
Yeah.
Just think, what does deprotonated or protonated mean?
Why?
Salt and the why?
Why did they make up that?
It's not made up. Can someone grab the door? Someone grab the door.
Someone had to make it up.
It's really good just to be able to think about these in 2 or 3 different ways. All right? It's the first time you've seen it. It's okay.
Where did you get the 0.67 and the 0.33?
So I was just assuming 1 on this one because I said that on number 3 it is 1/3 of its groups have been protonated. So if 1/3 have been protonated, then 2/3 have to be not protonated. So this was my third. That was a 2/3 not protonated.
And since you're not actually given a mass, it really doesn't matter.
When I
Right.
actually think about it,
So the 0.33 is the 1/3 that has been protonated. So my protonated is the 1/3. That's why I did the 0.33. And if 1/3 is protonated, that means 2/3 are not protonated. So I just took one, divided into 1/3 and 2/3. Cool?
So this
Yes.
is all of these notes. It's not like we're gonna have extra stuff that'll be on the next test. This is what's the test, right? All of these notes.
Yeah.
Okay.
There's-
so we have like a week and a half to prepare for this thing.
Oh yeah,
Oh, we got
lots of time.
It's not like we're gonna be adding and speckling more things in.
I mean, I might do a little bit more practice, just to like give you some more math practice.
Oh, yeah, that's fine.
Yeah.
There's no new content.
This is the majority of the content. Like this is it, right?
That's good.
It's pretty much it.
there's gonna be an exception.
Number 4.
I trust.
Number 4 is the fun one.
So good.
All right.
I love fun.
And in all honesty, I don't think you have enough room on this page to do it.
Oh,
Hey,
good.
Oh,
So get out a separate piece of paper.
we can make
I
it.
don't. Here's my work. All right.
Never mind. we
Here's
can't
my
make
work
it.
for number 4. So you guys can decide how small you can write.
We will not be making it.
All right. It's up to you. I just know that I cannot write that small because I write like a 3rd grader.
I was just gonna keep handing it to him until like he actually decided.
Can't do anything.
Okay, number 4. A lot going on here. Ethanoic acid with a pKa of 4.75. Find the pH of the solution that results from the addition of 40 milliliters of 0.040 molar NaOH to 50 milliliters of 0.075 molar ethanoic acid. A lot going on here, right?
Rice.
So we know there's going to be rice involved, right? What else is going to be involved? Henderson Hasselbalch,
Buffers.
right? Buffers. It's everything.
Because salt is NaOH. Just start.
Yes, which those T-shirts are sweet.
Wait, we have t-shirts?
The Student Action Leadership Team T-shirts are really nice.
No, those are the student leadership team.
Oh, Student Leadership Team. Sorry.
There's different, yeah.
Sorry.
Oh, I thought it was salt, and I was
My
like,
bad.
I don't have a
My bad.
t-shirt.
I was like, I don't have a t-shirt.
I was like,
It's
I want
this
one.
shirt. It's this stuff. This one.
How did you get elected to be on it?
It wasn't an election. It was just a chosen.
Chose, yeah.
Seth is chosen.
Nice.
I wasn't chosen.
He's chosen.
Seth, you should be.
All right, so I'm going to do number 4 here. So number 4. Where do you guys think would be a good place to start with this? Figure out your number of moles. I love that. All right? The first thing I'm going to do is figure out my moles of acid.
Yeah, yeah.
All right? That is the exact first thing I would do. So my moles of acid, we know how to do this. I'm going to take what? I'm going to take my milliliters, which is 0.05 liters, right? You guys okay with that?
Why do we need moles when we have malaria?
I've got 0.05 liters. Agreed?
You need moles.
Yes. Times, if I use the molarity, for every 1 liter, I have 0.075 moles.
Wait, why are we taking moles again?
I have to know how many moles I'm starting out with. All right?
Aren't we? Doesn't rice use molarity?
It can also use moles.
No.
In this case.
Rice can use anything. All right?
0.375.
Why aren't we? Eventually we're going to. All right?
That's-
Stay with me first. Just stay with me.
Sorry,
There will be some rice twice later. All right? You may have to rice twice later. Not today. Rice twice. So let's get our moles of acid. You're gonna see why. All right? You're gonna see why in a second. Stay with me. So this gives me 0.00375 moles of acid. 0.00375 moles of acid. Let's figure out our moles of base.
Yeah.
Easy. So this is going to equal what? 0.04 liters times, for every 1 liter, I have 0.04 moles.
Is this like a thing that you have to memorize which one's base and acid?
It tells you.
What?
Oh yeah,
It says.
We know NaOH is a base and
It says
ethanoic acid.
yeah.
Yes. So yes. So I'm going to say yes. You had to memorize that.
Okay.
From reading the question to here, you had to memorize it. Yes.
What if ethanoic acid is actually a base?
What did you get?
0.0016.
0.0016 moles of base.
Strong base.
Strong base.
Yes.
All right.
Isn't ethanoic a strong acid?
That's ethanoic.
Ethanoic is not a strong acid.
Not a strong acid.
So I have a weak
It's ethanoic
base.
base.
Weak acid, NaOH,
What?
strong base.
I have a strong base, but I do have a weak acid. Yes.
Buffer.
So what's a buffer?
So are we dividing
Base
this
acid.
by the
It's a
total?
base.
Not yet. All right. Not yet. There's a couple different places you could do this. All right. So here's how I started this. All right. So let's set up our equation.
Okay.
R, my reaction.
NaOH.
COO.
I have
What is that?
ethanoic acid. That's another name for acetic acid,
Really?
which is HC2H3O2.
Wait.
HC2H3O2. That's ethanoic acid.
Which is also CH3COOH.
Yeah.
Okay.
That's why acetic acid has 2 different versions on the back of your periodic table.
So I was just like, I don't agree.
Yeah.
It's just a science denier.
So, plus, do I care about the Na?
Probably not. We just want to know.
I don't think you would want to, would you?
We don't.
The Na is really just a spectator
Like,
ion,
it's
right?
just
Agreed?
It's unnecessary.
We're always observing.
I don't really care about the Na, right? It's really just the OH minus, because if it's NaOH, it's a strong base. It's completely dissociated, right?
Yeah.
So all of the hydroxide went to the hydroxide.
Yeah.
So
Agreed?
this is
I
like
feel
split
you.
ionic
It's kind of everything. All right?
H2O.
Is in equilibrium with H2O.
Personally, I care about NA.
If you want to write it out, you can. All right? But it's just not important. Plus
C2H3O2.
C2H3O2 minus.
Yeah. Facts.
Yeah, that looks right.
So,
Looks about right.
initial. And there's 2 different ways you can do this. I don't care how you guys want to do this. I'm going to show you how I did it. Initially, I'm starting out with how many moles of this? 0.00375 moles. How many moles of OH am I starting out with? 0.0016 moles. Is water part of my equilibrium? No. And do I have any C2H3O2 to start?
Not yet.
So plus 0. This is the tricky part. What's my change going to be?
Just like
Nothing.
nothing. One would expect minus X and minus X.
That's what you would expect.
I would guess I was wrong though.
Well, one of them,
It's minus.
No, Brendan's got this. I can feel it.
it's partial. So it's like something, a fraction of X.
I understand it.
I would look at what you start with and what you end up with.
Loses an H.
We end with?
And it adds an H for the other one.
We
What?
have pKa.
Okay, so think about this. What am I using up completely? I'm using all the OH, agreed?
Yeah.
Yes?
Yeah.
Because this is the weak acid, agreed? I know there's going to be some of this left on the other side. I think that's what Brendan said. All right? So my change is minus what? Minus 0.0016. Minus 0.0016 moles, because I'm using up all this OH. I have to figure out what am I using to figure out the change. Minus 0.0016 moles. This is why you can't do molar yet. All right? This is why you can't do molar, because it won't work. You need a quantity. Water's still not part of this. Plus 0.0016 moles.
This actually makes sense now.
That makes sense.
What?
Who doesn't?
So-
You're subtracting.
I have to- I know that I'm using up the OH, right? The OH is
I
gone.
don't think teaching you would
right?
be a good idea.
I'm using up all of this. So, because this is the weak acid, I'm going to have weak acid on the other side. I'm not using up all the weak acid
You just said
because it doesn't completely dissociate, right?
Yeah.
Yeah.
The weak acid does not completely dissociate, so I cannot use this for my subtraction.
It's like the limiting
I'm not gonna
reactant.
say that.
Let's just go with that.
Equilibrium.
Yeah.
Bro, why did we get rid of NA? We need to bring NA.
Because we don't need it.
Na is a spectator ion. It has nothing to do with what we're doing here.
Yeah.
All right?
I'm spectating.
Can I take a P of Na?
No.
No.
Oh, you could.
No.
Can I take a P from OH?
Yeah.
Equilibrium. So subtract.
0.0025.
0.00215 moles. 0,
Yep.
not part of it, and
0.0016.
0.0016 moles.
Oh, man.
So I made this like that was step 1. This was step 2. Step 3 is now to figure out total volume.
Add.
So V total is going to equal 40 milliliters because I'm adding these together, right? Plus 50 milliliters, which equals 90 milliliters, which is equal to 0.09 liters. So now I know my concentration at equilibrium. Agreed? So concentration of HA, right, is going to equal what in this situation? My concentration of
The ethanoic acid.
HC2, H3O2. So I'm kind of showing you what the HA is.
Wait,
Clicking right now.
HA is HC2H3O2.
I thought
That's the acid. HA is
Oh,
the
yeah.
acid, right?
Yeah.
That's going to equal 0.00215 moles divided by 0.09 liters. That will give you your molarity of acid at equilibrium. Your molarity of acid at equilibrium. What do you get?
0.0239 molar.
I got 0.024. 0.024. Yeah, you're right. 0.0239 molar. My concentration of A minus in this situation is going to be the concentration of C2H3O2 minus, right? I'm showing you the HA and the A minus. That's going to equal, 0.0016 moles divided by 0.09 liters. That's what Ashan was thinking.
Nice. That's what I was thinking.
That's what Brendan was thinking. What do you get for your molarity here?
I forgot how to
0.0178.
0.0178 molar. I now have a concentration of an acid, the concentration of the salt, and I have, what else? The pKa. So now, Henderson-Hasselbalch. Step 4. Step 4. No. Henderson-Hasselbalch is equal to pH plus pKa plus, wait, what?
pH equals.
Can you scoot your place?
Skip a step here.
I'm glad that you guys couldn't see that. So this is the Henderson-Hasselbalch equation. So pH equals pKa plus log of my concentration of A minus over my concentration of HA. pH equals, I have to take the negative log of whatever my pKa is, right? Oh, no, I don't. We have it. It's 4.75 plus, no taking a P here, log of quantity, 0.018 molar, divided by 0.0178 molar, divided by 0.0239 molar. pH equals what?
4.62.
Yeah, I got 4.62.
That's what I got too.
4.62.
Yes.
There's a lot going on there.
Less than.
A lot going on there.
Okay, what is log, Mr. Heller?
Log?
That's a really stupid question.
Logarithm?
Yeah, like what?
It's the inverse of x.
What is long?
Like what? Like I know how to put it in a calculator, but like what actually?
It's
does
just
work?
like
Log of 5 means 10 to the what equals 5. So
Right.
like log of 100.
10 to what power?
Think of the log of 100 then would equal 2.
10 to
Because
the
10
x.
to the 2 equals 100.
Right, which is why when we're undoing it, we're raising it to the negative power.
Oh, okay.
Like,
That makes no
ln
sense.
E equals 1.
Ah.
Because if
Log of
first
8,
E.
the overall equation would be if log of A equals B.
Yeah.
You guys are
then
such
10
math
to the
nerds.
B equals
We
A.
watched the video, that's
No, we still
We're
have
not done.
five.
Number 5.
We're not done. Number 5.
This better be an easy one.
It's not.
Is it the same?
Have fun.
Wait a second.
Do it.
I
No.
No?
I'll do it pass.
We're doing it together?
I would much rather.
Fine. This is very similar. How about this? I'll make you this deal.
I'm sorry.
You do number 5 over the weekend.
Facts.
We'll watch video announcements.
That's fine.
But let's finish this last little paragraph. Let's finish this last little paragraph. The capacity of a buffer is defined as its ability to continue to react with any extra or added acid or base added to it. The higher the concentration of the components of a buffer, the more it can absorb, and thus the higher its capacity. Thus the higher its capacity. Remember, the ratio of the components stays the same, so does pH.
So how does like a buffer work? Like we're talking about an experiment. Like,
Buffers
I'll show you.
can't,
All right, we'll do it. So over the weekend, do number 5. That's fair. We'll do number 5 over the weekend so we can watch video.